Hello, my darlings. We are live again. So, if you joined our previous live tonight, sorry about the interruption. I had to take a little bit of a break and I ate and I drank more water. We are back with this live stream. We will be covering physics topics. We have been reading from this book called Einstein's Cosmos, as you can see, written by Michio Kaku. And this is about how Albert Einstein's vision transformed our understanding of space and time. Now, as you know, we have already covered quite a few topics out of this book, and we have even looked at special relativity, all his work from the year 1905, where lots of major developments happened. Hi, Reese. Hello. Finally, my physics loving friends are here. Hello, Chloe. Hi, Reese. I went live a little while ago and there weren't a lot of people. And Bon Bon, hello. Is that Yash? Is that you, Yash? I see that I made you a moderator, so I'm wondering if that's you, Yash. Chloe said I missed it. I'm sorry. Oh, no worries. I think you were here, Chloe, for part of that live stream. So I have been talking about Einstein's work, and we kind of already covered special relativity and general relativity. Today we will be talking about his efforts towards grand unification theory, and it's a little bit complicated, but that's actually how we got string theory is sort of the story of this chapter. Okay, so hopefully you're ready for this, and we will get started with the reading and as well as the discussion. Let me go over to my iPad, which is charging, and I also charged the phone. Did you drink all your tea? I did, Chloe. I did. The tea is done. In fact, I'm not sure where I put my mug. I think it's in the sink already. So, yes, my tea is done. My food is done. I am in a better mood because I think I was a little bit hangry. So, yeah, it's done. And yeah, so let me go over to my iPad and share the live once again so people figure it out that we have gone live again. Hang tight. We will cover the full topic of grand unification theory from this chapter today. Hi, Victoria. Victoria Howard is saying, "Are you skibbity?" I'm not sure what that means, but thank you for asking, and feel free to clarify. Thank you. So let me put this down here so you can keep on seeing Baji. I might even keep the phone here actually so that you can see Baji the whole time, and also you can listen to my voice, hopefully without any glitches from the mic of the phone or anything like that. So we will get started. So this chapter is pretty interesting because it kind of talks about the challenges of Einstein too. It's important to note that even great physicists can have challenges when it comes to these very challenging topics. And I also liked the analogy that we talked about just now that you might have missed if you weren't here in the previous live, which has to, there's my live with a little bit of a lag. Skibbity, Google it. Well, I'm in the middle of a live, Victoria, so excuse me if I'm not able to Google this as rapidly as one might be able to normally. Feel free to tell me in the comments. Audio's a little low. Okay. Thank you for telling me, Reese. I might just have to hold the phone near me. Audio's a little low. Okay. Awesome. Thank you. Let me know if there's any other issues. Oh my goodness. So it's extremely important to note that we're dealing with sort of a complicated topic which might not, thank you, be super clear right away, but give it some time and let me explain and kind of go through it, okay? Baji, yes, thank you so much for being here. So we've kind of already seen sort of the motivation of this topic. I have mentioned in the past how there's really three big questions of the universe. The dark matter question: what is the nature of dark matter? We don't know. We know that it's needed because there is physical evidence for some missing matter, if you will, but we don't really know what that physically is, so we call it dark matter as a placeholder. Same thing for dark energy. We know that there is some energy of empty space or something cosmologically that was needed. It was called cosmological constant to kind of go against gravity and makes it so that the universe is not collapsing on itself. But again, we don't know the physical meaning of it. What is the physical sort of reality of this dark energy? We know that it is a placeholder again that is needed, but we don't know what it is exactly. And then, actually, in the last chapter that we looked at, where is Suji? Suji's over here. Here. She's over here. Suji's on the tree. Baji's here on the sofa. And Fuji's over there on the counter. So we've kind of seen that there was also another question of dark stars. So there's three dark things here. Dark matter. We still don't know what that is really. Dark energy. We still don't know what that is. Those are the top two questions of this universe that we still have to solve, actually. And then there's dark stars that we came across as well. And these are actually black holes, sort of a point like star. Remember how it was, I'm blanking on the name of the scientist. Wait a minute. I know this name. Schwarzschild, that's it. That's right. Schwarzschild's radius comes from Schwarzschild, the scientist who solved Einstein's equations for black holes or a point-like star and showed that they work very elegantly and completely for black holes. But at that time, there wasn't any physical evidence or observational evidence of black holes back in the early 1900s. So people were still kind of speculating as if that they don't exist, or maybe it's too fantastic. People actually thought it was too fantastic for such a thing to exist, and people kind of wrote it off actually. But turns out that this dark star is the only sort of dark thing from that time which is actually quite real. We have observed black holes. We know that they're real. They're very much a thing, and we do have physical evidence of them, and we have come leaps and bounds in terms of astronomy and astronomical sort of findings and observations and discoveries since that time. In the next 100 or so years up until now, enough to know that not only are there more galaxies in the sky, not just our galaxy, there's all these other, various, many galaxies, that the universe is expanding. Now we actually also know that the universe is not only expanding, but its expansion is accelerating, which gives further fuel to this need for like the dark energy concept I was talking about, which we still do not have a physical meaning of it. What is actually dark energy? We don't know, but we know it is something like that is needed, a placeholder like that is needed. So anyways, we've also, but even though with these, we have these unanswered questions, we do actually see a lot of progress in how we make observations and how we're able to collect evidence for various things, including black holes. So something fantastic that we discovered in the last chapter, which people thought at that time might not be real, but actually is real, is black holes. But moving on from that, now we're going towards the next topic, which is the grand unification theory. Now, this is where Einstein was hoping that there is some unified field theory that will basically unite gravitation theory with E&M, or electromagnetism theory. What is that theory? What is that sort of field, or something more foundational, something more basic that that can unite these theories? Now, also, we should note that at this time, this is sort of the 1915. See, we sort of read the beginning of this chapter already, but I'll summarize so that you can kind of get into what we're talking about. Chapter 7 of Einstein's Cosmos by Michio Kaku is unification and the quantum challenge. So we haven't really talked too much about quantum physics in this live stream, these episodes so far yet, because it wasn't a super focus of Einstein up until now. But you will see how we'll get into it at least a little bit going forward, because that also plays a role. Yes, get your popcorn ready. Thank you, Chloe, for all your comments. Thank you, M Animates. Thank you, Reese, for joining the live. Quantum stuff is baffling. Thank you. Thank you so much for your comments and chat messages. Really appreciate it, and really appreciate that you're here. Six cats. Thank you, Richard, for joining. We will continue our discussion. But in this book, so far, we have built up various topics. We've talked about classical mechanics, of course, that is the Newtonian mechanics that still actually is valid to a large extent in the realms of our physical world, because where it kind of breaks down is the extremely small, where quantum mechanics would be necessary, and in the extremely big, where cosmic scales are involved, and that is where special relativity and gravitational theory, or general relativity, the gravitational theory of Einstein, which is general relativity, those are needed in most of our realms, in the scales that we exist, human beings, trains, planes, automobiles. This type of world is okay with classical mechanics. We can even send spacecraft into space. We can send satellites into space by mostly doing classical mechanics. But where it breaks down is where it's very small, physics of very small, or quantum physics or quantum mechanics, and physics of very big, which is the cosmic scales, where you would need special theory of relativity of Einstein, as well as his generalized theory of relativity, which is general relativity, which explains the updated theory of gravitation. So we've kind of covered those here so far in the live stream. We've also covered some of his other work, such as the photoelectric effect. We've seen and we've mentioned quantum mechanics, but we haven't really gone into a lot of detail of quantum mechanics. So there's a reason for that. That is because it was kind of developing in parallel with Einstein. And you will see how, if you don't kind of embrace quantum mechanics, it will be difficult for you to understand or make progress in the part that he is trying to make progress in right now, in this chapter that we're in right now. That's why I wanted to kind of give you this little bit of a spiel here before we get into this chapter, okay? And kind of also recap what we've covered and what we have not covered. We've covered mainly classical mechanics, special theory of relativity, general theory of relativity, and the questions that it has brought up, such as dark energy, as well as black holes. Black holes, we know, is a thing. It's a good thing. We understand it much more now. And dark energy is something that we created the foundation for with his work, but we actually still don't know, even to this date, in the 21st century, what dark energy really is, okay? Reese is saying, the first time I read about the double slit experiment, it rocked my world. Oh, Young's double slit. Yes, I think it's absolutely crazy how the results can change if the experiment is observed. Yes, so we will get into some of that now in this chapter, so stay tuned. And I think you will enjoy it, because we're going to get into this sort of more crazy stuff now. It's the universe saying, whoa, hold on there. That's as far as you can go with understanding light and the universe. Yes. Hi, Chloe. Absolutely. So you will see how, without embracing quantum mechanics and some of the crazy things that come along with it, even Einstein was actually having a lot of trouble, because he was attempting to unify two things, electromagnetism and, his insights into light, as well as gravitation. And you will see some of the struggles he has to put it all together. Okay, so in 1905, almost as soon as Einstein worked out the special theory of relativity, he began to lose interest in it, because he set his sights on bigger game, general relativity. This is something we already covered in these live streams, so you can go listen to it again later on if you missed it. But stay here for now, because I think we will get into something interesting and kind of crazy. If he called it spooky, you know it's complicated. Yeah, in 1915, the pattern repeated itself. As soon as he finished formulating his theory of gravity, so that is the general relativity theory, he began to shift his focus to an even more ambitious project, the unified field theory, which would unify his theory of gravity with Maxwell's theory of electromagnetism. It was supposed to be his masterpiece, as well as the summation of science's 2,000-year investigation into the nature of gravity and light. It would give him the ability to read the mind of God. Einstein was not the first to suggest relationship between electromagnetism and gravity. Michael Faraday, working at the Royal Institution in London in the 19th century, performed some of the first experiments to probe the relationship between these two pervasive forces. He would, for example, drop magnets from the London Bridge and see if their rate of descent differed from that of ordinary rocks. Now, remember, Michael Faraday also did the science experiments in the lab. He was a very experimental scientist, a physicist, who basically gave us the changing electric and magnetic fields work. He literally observed those in the lab, and that's how we knew we had the experimental evidence of the fact that changing electric fields can turn into magnetic fields and magnetic fields can turn into electric fields. All of this was actually given to us by Faraday and his various observations. So, in hindsight, if some of his experiments seem kind of like simple or silly, well, these are the simple or silly things that you have to do in order to get to the truth sometimes. So, we have to be patient with this process. They're the same thing, I think, like static. So he would, for example, drop magnets from the London Bridge and see if their rate of descent differed from that of ordinary rocks. If magnetism interacted with gravity, perhaps the magnetic field might act as a drag on gravity, making the magnets fall at a different rate. He would also drop pieces of metal from the top of a lecture room to a cushion on the floor, trying to see if the descent could induce an electric current in the metal. Fuji, I love Fuji. Oh, thank you, Chloe. So these are so in the next couple of paragraphs, there are some experiments that Faraday did, and these unfortunately did not go anywhere. Okay, so that also must be kept in mind that other people also were trying to see if there is a relationship between gravitation and electromagnetism, and they were trying things to see it, to observe it, because you have to do the experimental science for it to be a real thing. But they were struggling. Molly love, hi. Hi, Molly. How are you, my love? Missed you. So he wasn't the only one. Einstein was not the only one who was thinking these thoughts. There were other scientists and they were trying too. Einstein once summarized his attitude toward unification by comparing marble and wood. So he kind of marble, thought Einstein, described the beautiful world of geometry in which surfaces warped smoothly and continuously. The universe of stars and galaxies played out their cosmic game on the beautiful marble of space-time. Wood, on the other hand, represented the chaotic world of matter with its jungle of subatomic particles, its nonsensical rules for the quantum. So he goes into some comparisons with marble and wood. These are not particularly... I was grounded. Oh gosh, Molly. Why? Tell us if you want to. There are some comparisons with marble and wood that Einstein makes here that Michio Kaku is talking about, the author. I don't find it particularly helpful, so I'll move ahead so that I can get to the part of the chapter where we left off in the previous live stream. But yeah, let's read this next part. This is actually helpful, so let's read it again. To Einstein, his strategy was clear: to create a theory of pure marble, to eliminate the wood by reformulating it solely in terms of marble. So he basically didn't like that sometimes with, understanding the quantum mechanics was becoming very necessary. Like, he knew that, atom was not the fundamental particle. Like, there was more complication because the atom still broke down into more fundamental particles. And so and he knows that ordinary matter is made up of atoms, which also he knows that ordinary matter interacts with gravitation, but then there is also the electromagnetism that's coming out of electric currents, which would be carried by the electrons. And he's just trying to find, where does this all relate with each other? What is the more fundamental theory that ties all this together? That's his struggle right now, and we will see this in this paragraph. Molly says, I punched a boy. Well, I hope he deserved it. Thus, if the wood itself could be shown to be made of marble, then he would have a theory that was purely geometric. For example, a point particle is infinitely tiny, having no extension in space. In field theory, a point particle is represented by a singularity, a point where the field strength goes to infinity. Punched a boy. Yeah. Okay, Molly says she has punched a boy, and we do hope that he has deserved it. So now he's talking about a singularity. A point particle is infinitely tiny, having no extension in space. In field theory, a point particle is represented by a singularity, a point where the field strength goes to infinity. Einstein wanted to replace this singularity with a smooth deformation of space and time. Imagine, for example, a kink or knot in a rope. From a distance, the kink may look like a particle, but close up, the kink or knot is nothing but a wrinkle in the rope. Similarly, Einstein wanted to create a theory that was purely geometric and had no singularities whatsoever. Subatomic particles like the electron would emerge as kinks or some kind of small wrinkle on the surface of space time. The fundamental problem, however, was that he lacked a concrete symmetry and principle that could unify electromagnetism and gravity. So now there wasn't just atoms, like I was saying. Atoms are also made up of protons, neutrons, and electrons create. He's fine. He's taking a nap. Electrons create electric currents, so therein we have electromagnetism, and he's trying to tie it all together and see if he can tie together gravity with electromagnetism. And so far, he cannot. And because remember, he also has an equation for gravitation. General theory of relativity gives you equations for gravitation, and he's trying to see where does it tie together with electromagnetism. That's what this chapter is about. Okay, the grand unification theory is about unifying all of those fundamental theories. As we saw earlier, the key to Einstein's thinking was unification through symmetry. With special relativity, he had the picture that guided him constantly, running next to a light beam. This picture revealed the fundamental contradiction between Newtonian mechanics and Maxwell's fields. From this, he was able to extract a principle, the constancy of the speed of light. So, this is what we covered already. Remember, special theory of relativity kind of discovered and also got further insight into this fundamental constant of nature, which is the speed of light, and he was able to kind of visualize this picture running next to a light beam and realizing, well, the speed of light is a constant no matter what you were doing. And that whole picture and that whole thought experiment gave him special theory of relativity, and he was able to picture this. Last, he was able to formulate the symmetry that unified space and time, the Lorentz transformations. Similarly, with general relativity, he had a picture that gravity was caused by the warping of space and time. So again, he had a thought experiment. Well, we understand magnetism as, to the extent of how we get it from electromagnetism, from the Maxwell's equation. So we do understand magnetism in the sense of the picture we have from electromagnetism theory. But maybe you're asking a different question. Like, we understand light, that it's an electromagnetic wave. Remember, because people knew about electric currents and they knew about magnetic fields, and then they discovered the relationship between those two, and then they found that light is an electromagnetic wave. It's the wave that's basically electric and magnetic fields oscillating is light. That's the nature, that's the wave nature of light. Then people were confused about how light is propagating in just empty, so-called empty space, because remember, they were like, oh, well, light comes to us from all these different stars and whatnot, and that seems to be in empty space that it's traveling through. And they, remember, had that confusion about ether, that there may be some medium that has to carry that wave. And then Einstein came up with special theory of relativity and kind of clarified all of that you didn't really need ether. So I would say maybe there is not everything that we understand about magnetism, but we have a picture of it in terms of Maxwell's equations. We do kind of understand in the realms of electromagnetism theory, and how light comes out of it. Like, special theory of relativity basically gives you the nice picture of electric and magnetic fields and how that's really the theory of light. So we understand that much. I don't know if there's something more fundamental that we don't understand, probably, right? But we kind of get it. But what he didn't get at this point was, where is this coming all together. Like he has equations that he gets out of general theory of relativity. Is there something that will kind of unify those equations with electromagnetism equations? Like Maxwell's equations should just fall out of GR, you know? That's where he's struggling. Because remember, special theory of relativity was can describe E&M basically. But remember, the problem with special theory of relativity was that it's only valid in the inertial frame, right? It was not valid anymore in the accelerating frame or in a frame with gravity. So that's what prompted him to work on general theory of relativity, because there you have gravity, and that is the more generalized theory that can explain gravitation. But now he's actually missing the E&M picture. He does not get it out of GR, basically, and he's trying to see if there's a way to do that. Okay, Reese, still with us? So similarly, with general relativity, he had a picture that gravity was caused by the warping of space and time. I'm just checking the comments to see if I missed something. Okay. Reese, are you still with us? Similarly, with general relativity, he had a picture that gravity was caused by the warping of space and time. This picture exposed the fundamental contradiction between Newton's gravity, where gravity traveled instantaneously, and relativity, where nothing can go faster than light. From the picture, he extracted a principle, the equivalence principle, that accelerating and gravitating frames obeyed the same laws of physics. Last, he was able to formulate the generalized symmetry that described accelerations and gravity, which was general covariance. The problem facing Einstein now was truly daunting because he was working at least 50 years ahead of his time. In the 1920s, when he began work on the unified field theory, the only established forces were the gravitational and electromagnetic forces. The nucleus of the atom had only been discovered in 1911, so this is quite new. Nucleus of the atom being discovered in 1911, and we're talking 1915, so within 3-4 years he's trying to do the unified theory, where we're still discovering subatomic particles. So this is all happening very fast for the unified field theory to be successful, because the timing is such where we're just now kind of discovering more complexities with the quantum world. So the nucleus of the atom had only been discovered in 1911 by Ernest Rutherford, and the force that held it together and was still shrouded in mystery. So the force holding the nucleus together, the strong force, was something that we didn't really know too much about yet in 1911, because, if you just discover the nucleus, then there's the things within the nucleus. The nucleus breaks down further into protons and neutrons, and what force holds those together, because we know that those are kind of repelling each other in terms of in terms of the electromagnetism theory, right? Because if something has the same charge, that should repel each other. But remember, in a nucleus, things of the same charge are often together. That's actually how we get the elements, because more and more protons in the nucleus gives us the heavier and heavier elements. Sometimes there's also neutrons in there. So there's a different force now at play within the nucleus of the atom, for example, that Einstein did not know about at that time when he's trying to come up with the grand unified theory. So that's why we have to bear with him through these years as we talk about these years, because remember, all of this is getting discovered at the same time, or sort of in parallel. So let me read this. I saw an interview with Richard Feynman when he was... Oh, I see. I saw an interview with Richard Feynman where he was asked what the force actually is that causes one magnet to repel or attract another, and he couldn't answer the question. Reese's Einstein. Kitty's so cute. Thank you, Molly. I remember hearing they only even know there's a nucleus since when they fired lasers at atoms, the light occasionally bounced off something So they theorized it must have a nucleus. Right. So we know that atoms have nuclei and that the nucleus has protons and neutrons depending on which nuclei or nucleus it is, depending on which element. So like lithium has or hydrogen has one proton and that's it. That's the nucleus. Helium has two protons and that's it. That's the nucleus. Lithium has three protons. Things like that. So basically, I think, I mean, I might be wrong. The magnetism, why it repels, I think it probably has something to do, honestly, now that I'm thinking about it, I could be, I could be wrong, but it's probably I think it's probably the strong force, if I'm not mistaken. I think magnets are just things that are the insides are like really aligned in a way where there's that North Pole South Pole thing happening in the macro where those poles, like the like poles, you know, repel and the opposite poles attract. It's probably something to do with I have to check, but I think we do have further insights on why the magnets repel or attract, if you're asking about that. But I thought you were asking about electromagnetism theory, and we do know how that behaves. At least we know about the electric and magnetic fields. Whether we know or not about the like or like and the opposite attracting or repelling, we know about the magnetic field, we know about the electric field, and we have a theory about how these fields behave and how things behave in the fields, and also how they change into each other, and that light comes out of all this as the electromagnetic wave. That's what I mean by that. We know electromagnetism theory, and we know about Maxwell's equations that describes electromagnetism. What Einstein is trying now here is to unify that with his gravitation theory, with his general relativity theory. I see. Okay, got it. They have accelerating magnetic flux going around them in a toroid pattern. They don't know what it actually is, though, just that magnets have concentrated magnetic flux. Right. Got it. Okay. That's something we might have to study more about. But basically, he wants the electromagnetism equations to come out of his general relativity. That's his efforts right now in this chapter. Okay? So we'll keep going. Without an understanding of the nuclear forces, Einstein lacked a crucial part of the puzzle. Furthermore, no experiment or observation exposed a contradiction between gravity and electromagnetism that would be the hook Einstein could grab onto. You can see the flux under a thing called a supercell. Oh yeah, Reese, that's right. You work with this stuff. So tell us more about your experience with electric and magnetic fields. You can see the flux under a thing called a supercell. It's beautiful. Really? It's a Friday, no way I'm studying. Hi, Molly. We're having fun. Think of this as a fun time. Reese, tell us more about this supercell. We don't, it was snow for today. I don't know about the supercell, so tell me more. I'll keep reading and I'll keep discussing this while you type that. So anyway, next we go to another person called Hermann Weyl. So Hermann was a mathematician who was inspired by Einstein's search for a unified field theory, made the first serious attempt in 1918. So now we're in 1918. At first, Einstein was very impressed. It is a masterful symphony, he wrote, while expanded Einstein's old theory of gravity by adding the Maxwell field directly into the equations. Then he demanded that the equations be covariant under even more symmetries than Einstein's original theory, including scale transformations. That is, transformations that expand or contract all distances. However, Einstein soon found some strange anomalies in the theory. For example, if you traveled in a circle and came back to your original point, you would find that you were shorter. but had the same shape. In other words, lengths were not preserved. In Einstein's theory, lengths could also change, but they remained the same if you came back to where you started. So there were some anomalies that came out of Wiles' theory that didn't quite make sense. So he had to abandon. He considered Wiles' theory, but he kind of did not. It did not last. It could not quite keep on going. Time would also be shifted in a closed path, but this would violate our understanding of the physical world. So there was something about Weil trying to, get this stuff to work out by putting electromagnetism equations into Einstein's and doing some math to make it work, but there were some anomalies. So he demanded that the equations be covariant under even more symmetries. And there were some anomalies that were not good. And so Einstein had to, even though he liked it at first, he had to kind of let it go. Because that can happen where you are trying something and, you're tempted to make some assumptions and make something work. But then the result of it is that some anomalies happen which are not really good at all. And so you can't really move forward in that direction anymore. Time would also be shifted in a closed path, but this would violate our understanding of the physical world. For example, it meant that if vibrating atoms were moved around a complete circle, they would be vibrating at a different frequency when they came back. Although Wiles' theory seemed ingenious, it had to be abandoned because it did not fit the data. In hindsight, we can see that the Wiles theory had too much symmetry. Scale invariance is apparently a symmetry that nature does not use to describe our visible universe. Okay, so he put in an invariance which was not quite right. It was not describing the physical world, so we had to abandon it. Okay, for the greater good, even if the math might have worked or something. Okay. In 1923, Arthur Eddington also caught the bug. Inspired by Wiles' work, Eddington and many others after him tried his hand at a unified field theory. So again, Einstein was not the only one who was trying to get to an unified field theory. There were other people too, and that's good because other people can come up with other ideas, and we can try everything. Why not? Because when you're trying to make something happen, the more the merrier. And even if some of the theories are wrong, even that is progress. Even say you come up with a theory, then you test it out. Either from the theory itself, you see certain things happen that would not be allowed in the physical reality, or you test it out in actual experimentation and it comes out that it's not good. And even that is progress. Even a negative result is a result. Even something saying that, hey, this can't happen is still a result in experimental science, and it's very much needed. So like Einstein, he created a theory based on the Ricci curvature. So now we're talking about Eddington. He created a theory as well based on the Ricci curvature. But the concept of distance did not appear in the equations. In other words, it was impossible to define meters or seconds in his theory. The theory was pre-geometrical. Only in the last step would distance finally appear as a consequence of his equations. Electromagnetism was supposed to emerge as a piece of the Ricci curvature. The physicist Wolfgang Pauli did not like this theory at all, stating that it had no significance for physics. Einstein also panned it, thinking it had no physical content. So it's all very well to come up with some math that may math out, but another to kind of have some physical content. And especially if your math is leading to things that are not physically, true, then those things get kind of abandoned. But this is all the things that was kind of going on at that time. Okay. So, but what really rocked Einstein to the core was a paper that he saw in 1921. So now we're in 1921. So he started in 1915. It's been 6 years already, and he's had a few failed attempts at unifying these theories. So this was written by an obscure mathematician, Theodor Kaluza, from the University of Königsberg. Kaluza suggested that Einstein, who had pioneered the concept of the fourth dimension, add yet another dimension to his equations. So remember, when Einstein had suggested that we consider everything to be 4 dimensions, which is the 3 space dimensions and the fourth being the time dimension. Remember that whole thing about the space-time relativity and space-time being relative, and uh, the length contraction, the time dilation, all of that stuff that comes out of special relativity. Basically, he pioneered this theory that we should be thinking about 4D. It's really about four dimensions, the space dimensions as well as the time dimension. So it kind of opened up people's minds to the possibility of, okay, well, it's really about dimensions. Which dimension are we in? Like, are we in 3D, 4D, 5D? Like, it kind of opened up people's minds towards thinking about more dimensions. And what Kaluza did, sort of as an obscure mathematician, is to consider a fifth dimension, something that Einstein had not yet considered. So that's what we're going to get into now. Yes, Reese, you caught it. Oh, sorry, Baji. I got excited. Let me read your comment earlier. I'm losing my supercell, says Molly. It's ferrofluid or liquid containing iron, basically. Got it. Yeah, ferrous. I think they even use biological liquids, and a thin layer of it is squashed between two layers of glass discs, and then it has lights around. Then, then it has lights around the. Molly says, see, perimeter. Oh, around the perimeter, so that when you place it over a magnet, you can view the field. Oh, wow, how nice. That sounds really cool. I feel like we're getting into the birth of string theory here. Yes, Reese, are you ready? We are getting into the birth of string theory here. So I hope you guys are ready. It's very exciting. And I will just say that string theory is generally researched by people who teach the GR class. So when I took GR in grad school, the guy who was, the professor who's teaching the GR class is like a string theory specialist and a string theory expert. And so for for you to be a string theorist, you first have to obviously start with GR and be very, very, very comfortable with all the notations and mathematics of GR. And once you take that forward, you get something like string theory. So that's where we're headed. That's where we're headed. So anyway, Kaluza suggested that Einstein, who had pioneered the concept of the fourth dimension, add yet another dimension. Did you say something? Let me see. No, you didn't yet. Okay. Yet another dimension to his equations. Kaluza began by reformulating Einstein's own general relativity. None of us do compared to host. What do you mean? I feel like we're getting into the birth of string theory. I think I had too much energy drinks. What? Who, me? Oh my gosh. Aw. Kaluza suggested that Einstein, who had pioneered the concept of the fourth dimension, add yet another dimension to his equations. Kaluza began by reformulating Einstein's own general relativity in 5 dimensions, 4 dimensions of space and 1 dimension of time. So now listen to this. This is going to be so cool, guys. This takes no work at all, since Einstein's equations could easily be formulated in any dimension. Because remember, with general relativity, you can basically, if you're comfortable with multiple dimensions, if basically you can just put in more, everything is kind of compact in the equation, right? So you can just add another dimension basically, and the equations should just, still work. And that's basically what Baji's mom, yes. My name is Oindri, Oindree. That's my first name. I have a book on gamma ray bursts if you're interested. We can read that too sometime. So, basically, Einstein's equations are so freaking amazing that Kaluza took them and added one more dimension, okay? And we will see where that takes us, okay? So ready for this journey? Let's go. So this takes no work at all, since Einstein's equations could easily be formulated in any dimension. Then, in a few lines, Kaluza showed that if the 5th dimension is separated from the other 4, Einstein's equations emerged along with Maxwell's equations. Oh, sorry, Baji. Sorry. Do you see how exciting that is? Do you see how exciting that is? Like he just added a fifth dimension because you can in general relativity, and he basically separated it from the other four as if it's like sort of this other thing that's not quite the same, but he added one more. And Einstein's equations emerged along with Maxwell's equations. In other words, Maxwell's equations, the horrible set of 8 partial differential equations memorized by every engineer and physicist, can be reduced to waves traveling on the fifth dimension, guys! Fifth dimension! That's so beautiful. To put it another way, Maxwell's theory was already hidden inside Einstein's theory if relativity were extended to 5 dimensions. Oh, Einstein was surprised by the sheer audacity and beauty of Kaluza's work. He wrote, Kaluza, he wrote to Kaluza, the idea of achieving unification by means of a 5-dimensional cylinder world never dawned on me. At first glance, I liked your idea enormously. A few weeks later, after studying the theory, he wrote, the formal unity of your theory is startling. In 1926, the mathematician... But why not? Reese, we'll get into it. Just hang tight. You'll see it's going to make so much sense in just a second. You'll actually see that. So I am actually a big fan of this in the sense that we experience 4 dimensions, but that does not mean that there couldn't be more dimensions. It's okay that we cannot think of it or imagine it very easily, but that doesn't mean that it does not exist. Reese, ready for this? There's going to be an amazing analogy in just a second here, and you'll see how it's actually, I feel like it's almost like, why not, with having more dimensions? I don't know. We'll see. But listen to this. Okay. Deep breath. I'm excited. Analogies for the win. Yes, exactly. So, at first glance, I liked your idea immensely, is what Einstein is saying. A few weeks later, after studying the theory, he wrote, the formal unity of your theory is startling. So this is the thing. He had a formal unification of Maxwell's equations with Einstein's equations. Can you believe that? That's freaking amazing. That's what Einstein would have wanted, but he just didn't know how it would be physically possible because we don't physically see this 5th dimension, right? So mathematically, Kaluza introduced a 5th dimension, and he did it in a way that was basically possible, and he united Maxwell's equations with Einstein's equations, as in Maxwell's equations now came out of Einstein's equations. And that's what Einstein wants. Einstein wants a general understanding of the universe that can just explain everything. All the fields, all the forces should just fall out of his equations. He wants to generalize it to the point where from his equations, you can just derive Maxwell's equations. That's what we mean when we talk about unification. That's what his goal is. He wants it to be general, the general story, the general equations of the universe, It's not supposed to be just for one thing. When he writes the general theory of relativity, it should also explain E&M, is what he's saying, because he's ambitious. Why not? He doesn't want a theory for just gravity. Gravity, I mean, that's only one thing. It's a big thing, but it's only one thing. So, but then Kaluza did this 5th dimension thing and got the E&M equations to fall out of Einstein's equations, which is freaking awesome. Like that's startling. But anyway, in 1926, the mathematician Oscar Klein generalized Kaluza's work and speculated that the 5th dimension. Okay. This is where it gets real. All right. Listen to this. So in 1926, the mathematician Oscar Klein generalized Kaluza's work and speculated that the 5th dimension was unobservable because it was small and possibly linked to quantum theory. Kaluza and Klein were thus proposing an entirely different So this is Klein, right? Oscar Klein in 1926. So Kaluza had done the thing where he had done the math and made Maxwell's equations fall out of Einstein's equations by simply adding a fifth dimension in an elegant, amazing way, which startled Einstein. And then Klein is saying, hey, guess what? That fifth dimension that Kaluza included to make it all work, maybe maybe it is there, but obviously we don't experience it. So what's the deal with that? Because we experience only four dimensions. But then Klein is saying maybe it is very small and possibly linked to quantum theory. So Kaluza and Klein were thus proposing an entirely different approach to unification. To them, electromagnetism was nothing but vibrations rippling along the surface of a small, teeny-weeny fifth dimension. So they're saying that maybe we, us human beings, don't really experience this fifth dimension because it's tiny. It's a teeny weeny little, little teeny weeny dimension that we don't experience. It's not important in our physical reality. And so it might be very hard to measure, but that doesn't mean that it doesn't exist. And here's the analogy. For example, if we think of fish living in a shallow pond, yes, four dimensions meaning space-time. Space-time, so three dimensions of space, and the fourth dimension is time. So we, us, all of us, we experience four dimensions for sure, right? We experience length, width, height, and time. So, right, Reese, we know that like our physical reality is made up of four dimensions. We know how to experience a length, a width, a height, X, Y, Z, and then also time, T, right? Those are our four dimensions. What Kaluza did was write Einstein's equations with adding a fifth dimension. But he kept it a little bit separate and he made it all work so that Maxwell's equations just came out of Einstein's equations now if you included this fifth dimension. But then the problem people are having, of course, with this fifth dimension is that, well, we don't experience it. Like we human beings, us, Baji, Fuji, Suji, we don't know about this fifth dimension. So what's going on with that, right? What is this fifth dimension? Like if it's in the equations, it has to have a physical meaning. Why don't we experience it, right? How are we going to prove that it exists? So then this other guy, Oscar Klein, who is teaming up with with Kaluza, said, well, maybe this fifth dimension, which so elegantly makes it work, it elegantly united Einstein's equations with Maxwell's equations. Maybe this fifth dimension is a very tiny, small one. Maybe it is something that we can't really experience as us, humans and kitty cats. We can't experience the fifth dimension, but that does not mean that it does not exist. It can exist, and we just don't get it. We just don't see it. So now listen to this analogy. This will help a lot. Everybody listen up. For example, if we think of fish living in a shallow pond, swimming just below the lily pads, the fish might conclude that their universe was two-dimensional. They can move forward and backward, left and right, but the concept of up into the third dimension would be alien to them. They don't really move up. They're always kind of they're in a shallow pond, so there's not a lot of, height, and they have the lily pads above them. They don't really see much, up from them. So they move forward, backward, left, and right, okay? If their universe was two-dimensional, then how might they become aware of a mysterious third dimension? So he's basically saying, these people, Kaluza, Klein, they're basically saying that maybe we do live in a fifth dimension. Reese, Molly, and Chloe. Maybe we live in 5 dimensions. It's just we experience 4 of them. This fifth one is a small, teeny-weeny one that we don't experience much, just like the fish don't experience the up dimension because they're in this shallow pond with the lily pads on top. If their universe was two-dimensional, then how might they become aware of a mysterious third dimension? Imagine that it rains one day. Tiny ripples in the third dimension move along the surface of the pond, and they're clearly visible to the fish. As these ripples move along the surface, the fish might conclude that there was a mysterious force that could illuminate their universe. Similarly, in this picture, we are the fish. We conduct our affairs in three spatial dimensions, unaware that there could be higher dimensions existing just beyond our senses. The only direct contact that we might have with the unseen fifth dimension is light, now viewed as ripples traveling along the fifth dimension. So, because there's this light thing is coming in because now, Kaluza did the fifth dimension thing, and Maxwell's equations came out of it, and Maxwell's equations describe electromagnetic waves, right? So they'd need a periscope. Yeah. So that's what's going on. They're suggesting maybe human beings, maybe we in our physical reality, there is a fifth dimension, a fifth, actually spatial dimension, that too. And maybe we just don't experience it because it's tiny, because it's something that is beyond our regular senses. I mean, some people say they have a sixth sense, right? So some people's extra sense might be from the extra dimension. Maybe there is an extra dimension, and maybe some people are more sensitive to it than others. That's just me, though. That's just me speculating. So, there was a reason why the Kaluza-Klein theory worked so well. Recall that unification through symmetry was one of Einstein's great strategies that led to relativity. In the Kaluza-Klein theory, electromagnetism and gravity were united because of a new symmetry, five-dimensional general covariance. Although this picture was immediately appealing, unifying gravity and electromagnetism by introducing another dimension, there was still the nagging question, where was this fifth dimension? So people were having difficulty to accept this because ultimately physics is an experimental science. If you couldn't prove that there was a fifth dimension, then it would sort of still be a speculation. This introduction of the fifth dimension to make it work, like with the Kaluza-Klein way of making Einstein's equations work, would kind of still be speculative. It would not be totally. It would not be totally acceptable. People would still kind of speculate on it. No experiment has ever, even to this day, picked up evidence of any higher dimension of space beyond length, width, and height. So not only do we live in, of course, this physical dimensions being just the XYZ or the length, width, and height, so far we haven't done any experiments that have illuminated that there might be another dimension. Okay, now that could just be that we haven't designed an experiment well enough to be able to pick that up because we live mostly in these three dimensions plus time. So it might be very difficult for us to prove that there is another dimension because, well, we just don't live in higher dimensions than this. If these higher dimensions exist, then they must be extremely small, much smaller than an atom. So that's what people thought. And even now, I think people think this, like, maybe these dimensions are very small. Maybe they're sort of subatomic level small to the point where we're not. Because think about it. Do we really experience atoms and subatomic world in our regular lives? No, not really, right? Like we don't really experience something so small. And so maybe these dimensions are something so small that we don't really experience it. But could we pick it up, though, in some experiment, and then it would prove that that dimension exists? I think that's what people are trying. Or extremely large, maybe. Yeah, absolutely. You guys are not the ones who had to stay up for the entire day. Oh my gosh. Hi, Molly. For example, we know that if we release chlorine gas into a room, its atoms can slowly permeate all the nooks and crannies of any room without disappearing into some mysterious extra dimension. We know, therefore, that any hidden dimension must be smaller than any atom. In this new theory, if one makes the fifth dimension smaller than an atom, then it is consistent with all laboratory measurements, which have never detected the presence of the fifth dimension. So even now, I don't believe that we have found this fifth dimension. I could be wrong. Maybe we have, but I think that would be pretty big news. Kaluza and Klein assumed that the fifth dimension was curled up into a small ball, too small to be experimentally observed, like this Baji. So Kaluza and Klein said that the fifth dimension was a little kitty cat who is curled up, like Baji here. So, so they're saying that it's hard to observe it, hard to figure it out because it's a curled up, elusive dimension. Okay? Although the Kaluza-Klein theory was a fresh, intriguing approach to unifying electromagnetism with gravity, Einstein eventually had doubts. The thought that the fifth dimension might not exist, that it might be a mathematical fiction or mirage, bothered him. So he was bothered by the fact that, oh, their food's about to fall, so you'll see them jumping up. You'll see that basically, oh my gosh, lots of food has fallen. They're getting their snack, but we'll continue. Basically, Einstein was a little bit worried that, well, this fifth dimension that was needed to make this Maxwell's equations fall out of his equations, making it general, was could be a mathematical fiction if we were never able to prove it out, right? And I believe that is still sort of the challenge of something like string theory, which is that it's so difficult to prove it out that these dimensions actually exist, that even though the equations work out, but do we know that this is real or is it just fiction, mathematical fiction? So I can't visualize it without some sort of analogy. Well, I think the fish analogy was the analogy where the fish don't know about the up dimension because they don't experience it. So similar with us. Like, just imagine there's something, another dimension, that we just cannot experience very easily. It is let me read your comments. Okay. Chloe and Molly, thank you for your chats. I think it's just something that we cannot experience with our usual senses most of the time. But I think the fish one is basically an example to show you that that could happen. So anyway, the thought that the fifth dimension might not exist was bothering him, okay, with Einstein. Maybe he had the same issue as Reese here, where he's like, well, if we can't experience it and we don't know how to experience it, if you can go left, right, up, down, and everywhere in between, what else could be possible? That is the question. Also, he had problems finding subatomic particles in the Kaluza-Klein theory. His goal was to derive the electron from his gravitational field equations and try as he could find no such solution. In hindsight, this was a tremendous missed opportunity for physics. If physicists had taken the Kaluza-Klein theory more seriously, they might have added more dimensions beyond 5. So basically, they had added 5 dimensions, right? But then later on, as we know, with the string theory, there's going to be more. And basically, what Michio Kaku, the author, is saying is that, well, they may have given up on the 5-dimension thing too quickly. Just because you cannot experience it does not mean that it's not there, right? We are only human beings after all. So we might be designed in a way where we can only spatially mostly experience three dimensions, but that's not to say that there can't be more, right? There could be more. We might have to stretch our imaginations and it might be uncomfortable. But the fact is that what we experience does not have to be the limit of this physical world or of this universe. It might be just a fraction of what the universe is, right? So, maybe. I don't know about the multiple universes. That could be, but I think it's more to do with just having another dimension that we don't uh, just just think about, like, we experience XYZ. What if there was another dimension spatially that we just don't experience? My brain is at the moment, Molly. Yeah. Hang tight, guys. His goal was to derive the electron, or sorry, where were we? As we increase, if your mind is not feeling a little bit bendy, then we're not close enough to string theory. I mean, what do you think string theory is? Do you think it's doable by most people, and that that it's very simple? Of course not. It has we if your mind should be feeling a little bit more, your brain should be feeling a little bit more squishy by the end of this, okay? Bend your brain and keep on listening, and think about more than three spatial dimensions, okay? I'm sure you'll have progress with this. So, if physicists had taken the Kaluza-Klein theory more seriously, they might have added more dimensions beyond five. As we increase the number of dimensions, Maxwell's field increases in number into what are called the Young-Mills fields. Klein actually discovered the Young-Mills fields in the late 1930s, but his work was forgotten because of the chaos of World War II. So wars got in the way of this five-dimension progress. Wars were very, disruptive to physics progress. It would take almost 2 decades before they were rediscovered in the mid 1950s. So we rediscovered more dimensions in the mid 1950s, and by rediscovered meaning like more work was being done again. Oh, really? Oh, okay. I'm glad that you guys are having fun. These young meals fields now form the foundation of the current theory of the nuclear force. Almost all of subatomic physics is formulated in terms of them. So, by the way, if you want to learn more about the subatomic fields, subatomic physics, like the strong forces and all that, so Baji's going to the bathroom. He'll be back soon. Hi, Shoham. Hello, how are you? If you want to learn more about this, you have to be comfortable with the Young Mills fields, or at least accept them as reality or something. Show your face. Do I owe you that, Shoham? Chloe says, "Are you okay? Are you okay, Molly?" Okay. After another 20 years, the Kaluza-Klein theory would be resurrected in the form of a new theory. String theory, now considered the leading candidate for a unified field theory. So, Reese, the unified field theory is basically, at this point, the leading candidate for a unified field theory is string theory. So, and this is how we got there. So you guessed right. This whole fifth dimension thing, and maybe even needing more dimensions, is string. Is leading us towards string theory. And of course, string theory is where you might want to bend your mind and accept that there might be dimensions that we cannot experience or do not experience very easily, but they do exist. It's a theory still because it's not proved out with experiment, but I do think, especially because the math works so well, and especially because, oh, there's Baji. And especially because, I mean, we're pretty limited, right? And like some people do have, I mean, there's people who are like psychics and stuff who do experience more things, and they're sort of like, I don't know, maybe we do have some sensitivity to other dimensions and we just don't know it yet. Maybe it's not very consciously known yet. You know what I mean? But I don't think that it's a completely like a sounds like a nightmare. Okay. I don't think it's completely, improbable or implausible that there could be more dimensions. Like what we experience doesn't have to be it. That cannot, that's probably not it. Anyway, sounds like a nightmare because it is. Okay. Einstein hedged his bets. If the Kaluza-Klein theory failed, so anyway, what Einstein now came to do is that he is looking at the Kaluza-Klein theory, right? He knows that this works out well with the math and the equations fall out, and there is this little detail that you need an extra dimension in order for it to work. I knew a girl once who thought that our dreams were us experiencing other dimensions. Yeah, could be. I don't know. I think this other dimension stuff, it might just be something subtle, It doesn't have to be. It doesn't have to be something, I don't know, strange. It's just something. It is what it is. Einstein hedged his bets because he was basically a little scared. I think he feared that, well, if we believe in this fifth dimension stuff and it never pans out and we can never prove it, then it's almost like supporting something that is speculative and it's not real science. So he hedged his bets. If the Kaluza-Klein theory failed, then he would have to explore a different avenue toward the unified field theory. His choice was to investigate geometries beyond Riemannian geometry. He consulted many mathematicians, and it became quickly obvious that this was a totally open field. In fact, at Einstein's urging, many mathematicians began to look into post-Riemannian geometries or the theory of connections to help him explore new possible universes. New geometries involving torsion and twisted spaces were soon developed as a consequence. These abstract spaces would have no application to physics for another 70 years until the arrival of superstring theory. So guess what? He turned to mathematicians to give him like non-Riemannian geometries and math that can help him out. But those didn't really go anywhere too much until superstring theory. So that whole stuff that we were discussing that people were having a hard time sort of accepting, I think it's much more accepted now. String theory is a thing. People research it. Superstring theory is a thing. Like, you just have to be ready to bend your brain a little bit, and then it's just breathe. Breathe. Yes, your arm might be lost, but then just breathe into it. Breathe into it. Feel into it. Feel into more dimensions. Working on post-Riemannian geometries was a nightmare, however. Einstein had no guiding physical principle to help him through the thicket of abstract equations. Previously, he used the equivalence principle and general covariance as compasses. Both were firmly rooted in experimental data. He had also relied on physical pictures to show him the way. With the unified field theory, however, he had no guiding physical principle or picture. So I think it was very difficult for him to picture this because, as you were saying, it's difficult to picture more dimensions than what we live in. And it's difficult to picture things that are not really easily supported by experimental data. If he theorizes something and then he can prove it out with an experiment, then it stands true. But if he theorizes something and he has no clue how to ever test it out, then that's actually very difficult. But then some people, I will say, are very comfortable with theorizing. They're comfortable with not knowing with the experiment. These people are called theorists. And these people do exist. In physics, there's lots of them. And many of them, they don't really care if something is really proved or not with experiment. And their theories, they're strong enough theorists. They can do the math better than other people. And honestly, you can have a career as a theorist, So there is such a thing. So curious, My cousin is laughing so much. Okay. So curious was the world about Einstein's work that a progress report he gave on the unified field theory to the Prussian Academy was reported to the New York Times, which, oh look, Suji has come out of a different dimension. Hi, Suji Boobly. Suji has just experienced a different dimension and has jumped out. So people were so interested in this unified field theory stuff that they were asking Einstein to give a progress report on it, because now it's been some years that he has been trying, right? So it's like, okay, can you give us an update, and I will yeah, here's Suji, and we will publish it in the New York Times. So this stuff was, popular enough. Oh, look at that. Suji Bubbly. This stuff was popular enough where even the New York Times was wanting to publish on it. I wonder if AI will be able to theorize any better than people in the future. Yeah, possibly. Sachi Mama. Soon there were hundreds of reporters swarming outside his home, hoping for a glimpse of him. Eddington wrote, "You may be amused to hear that one of our great department stores in London, Selfridges, has posted on its window your paper. The 6 pages pasted up side by side." So his progress report that he wrote was being pasted up on the store's window, so that passersby can read it all through. Large crowds gather around to read it. Einstein, however, would have traded all the adulation and praise in the world for a simple physical picture to guide his path. So he really relied on these simple physical pictures and physical evidence and experimentation to prove out his theories and to understand his physics. Even if the experiments were thought experiments, he was relying on what you would call what is basically an experiment, if you will, in order to understand the universe. But now he couldn't rely on that anymore, possibly because, even Einstein has his limits. He can't probably imagine all these higher dimensions too well, or find a way how to kind of make an experiment with them. I don't think there will be much to differentiate us from machines or computers in the future, only things like emotions. Good news, it came off. Bad news, I cut my arm. Yeah, I don't know. I think so, yeah. Emotions and... yeah, I don't know. Perhaps. Gradually, other physicists began to hint that Einstein was on the wrong track and that his physical intuition was failing him. One critic was his friend and colleague Wolfgang Pauli. So you might know Pauli from his Pauli's exclusion principle. Wow. Suji is having zoomies. I'll give you a minute to look at Suji here. So Pauli, you know him from the Pauli exclusion principle. Hopefully, we will now listen to some we will now listen to some comments from Pauli. So, oh, the kitty cats are playing. So, so Pauli was a critic of this part of Einstein's work. He once said of a misguided physics paper, "It's not even wrong." To a colleague whose paper he had reviewed, he said, "I do not mind if you think slowly, but I do object when you publish more quickly than you think. So Pauli was kind of roasting his, peers and colleagues at the time. After he heard a confused, incoherent seminar, he would say, "What you said was so confusing that one cannot tell whether it was nonsense or not." When fellow physicists complained that Pauli was too critical, he would reply, "Some people have very sensitive corns, and the only way to live with them is to step on these corns until they're used to it." His His impression of the unified field theory was reflected by his famous comment that what God has torn asunder, let no man put together. Ironically, later, Pauli would also catch the bug and propose his own version of the unified field theory. So basically, he was kind of critical of Einstein's efforts for the unified field theory, but at the same time, probably inspired by it to work on it himself as well. Okay, so we're gonna keep going. Got it. Pauli's view would have been endorsed by many of his fellow physicists who grew increasingly preoccupied with the quantum theory, the other great theory of the 20th century. The quantum theory. So now we're getting into some of the quantum theory stuff, okay? Sounds like he was a master at dissing or burning people. What a guy. Yeah, I don't know if you're familiar with the Pauli exclusion principle. It's actually very important. So he was a contributor to the quantum physics stuff. And so we're going to get into that a little bit now. But basically, all of that is to say that Einstein was having trouble with his grand unification theory, and it was difficult. And he was impressed with the fifth dimension attempt at unifying things, and it was actually very successful, sort of. But instead of kind of embracing it and embracing that we might need these higher dimensions in order to unify things, he kind of might have given up on it too soon, because I think later on people did embrace it. And there's these people called string theorists, and maybe, if he had embraced it more, maybe that field could have seen more progress sooner, because you need people to work on these things in order to make the progress, right? So I think that's what the author is suggesting here. Hi, Eric. Sounds like he was a master at dissing. Yeah. Pauli's view would have been endorsed by many of his fellow physicists who grew increasingly preoccupied with the quantum theory, the other great theory of the 20th century. So we really haven't touched on or spent too much time with the quantum theory at all. And hopefully now we'll get into it a little bit more. I'm just wanting to check that these comments I didn't miss anything about the physics. Okay. So, Pauli's view would have been endorsed by many of his fellow physicists who grew increasingly preoccupied with the quantum theory, the other great theory of the 20th century. The quantum theory stands as one of the most successful physical theories of all time. It has had unparalleled success explaining the mysterious world of the atom, and by doing so has unleashed the power of lasers, modern electronics, computers, and nanotechnology. Ironically, however, the quantum theory is based on a foundation of sand. In the atomic world, electrons seemingly appear in two places at the same time, jump between orbits without warning, and disappear into the ghostly world between existence and non-existence. As Einstein remarked as early as 1912, the more success the quantum theory has, the sillier it looks. So in quantum theory, all of this is possible. It's not something where you can be very limited in what you are thinking. My favorite shirt got stained. So, yeah, some of the bizarre features of the quantum world were made apparent in 1924 when Einstein received a curious letter from an obscure Indian physicist. Wait, sorry, I touched something by mistake. Okay, I think it's fine. Some of the bizarre features of the quantum world were made apparent in 1924 when Einstein received a curious letter from an obscure Indian physicist, Shotendranath Bose. This guy is from the same city as I am from, Kolkata, whose papers on statistical physics were so strange that they were flatly rejected for publication. Wow. Bose was proposing an extension of Einstein's earlier work on statistical mechanics, searching for a fully quantum what? Searching for a fully quantum mechanical treatment of a gas, treating the atoms as quantum objects. So this Bose Einstein condensate stuff, I don't know if you're familiar with, but that's what we're going to read about here in a little bit. So apparently, I didn't know this actually, that Shotendranath Bose was rejected so much for publication, but his work is remarkable. At least now it's considered to be very good. Bose was proposing an extension of Einstein's earlier work on statistical mechanics, searching for a fully quantum mechanical treatment of a gas, treating the atoms as quantum objects, just as Einstein had extended Planck's work to a theory of light. Bose was hinting that one could extend Einstein's work into a fully quantum theory of atoms in a gas. Einstein, a master of the subject, found that though Bose had made a number of mistakes, making assumptions that could not be justified, his final answer appeared to be correct. Einstein was not only intrigued by the paper, he translated it into German and submitted it for publication. So he then extended Bose's work and wrote a paper of his own, applying the result to extremely cold matter that hovers just above the temperature of absolute zero. Oh, here's Baji. So he stole his work. I think he gave him credit. I don't know. I think, I'm not sure, but I think he probably gave him credit. He might have just translated it and then republished it and hopefully gave him credit. I mean, there is a thing called Bose-Einstein condensate. So hopefully he... Printing guy, yeah. Hopefully he got the credit. I think he did. Bose and Einstein found a curious fact about the quantum world. All atoms are indistinguishable. That is, you cannot put a label on each atom, as Boltzmann and Maxwell had thought. While rocks and trees and other ordinary matter can be labeled and given names, in the quantum world, all atoms of hydrogen are identical in any experiment. There are no green or blue or yellow hydrogen atoms. Einstein then found that if a collection of atoms were supercooled to nearly absolute zero, where all atomic movement almost ceases, all the atoms would fall down to the lowest energy state, simply creating a single superatom. Wow. These atoms would condense into the same quantum state, behaving essentially like a single gigantic atom. He was proposing an entirely new state of matter never seen before on Earth. However, before the atoms could tumble down to the lowest energy state, the temperatures would have to be fantastically small, much too small to be experimentally observed, about a millionth of a degree above absolute zero. At these extremely low temperatures, the atoms vibrate in lockstep, and subtle quantum effects only seen at the level of individual atoms now become distributed throughout the entire condensate. Wow. Like the spectators at a football game who form human waves that sweep across the stands as they stand up and down in unison, the atoms in a Bose-Einstein condensate act as if everything is vibrating in unison. But Einstein despaired of ever observing this Bose-Einstein condensation in his lifetime, since the technology of the 1920s did not permit experiments near temperatures of absolute zero. Yeah, it is interesting. In fact, Einstein was so ahead of his time that it would be about 70 years before that prediction could be tested. So Bose-Einstein condensate is much more, acceptable now. We know about it. And when I was taking statistical physics and learning about Bose-Einstein condensation, it wasn't something regarded as crazy. Like, it was interesting, but it's accepted. In addition to Bose-Einstein condensation, Einstein was interested in whether his principle of duality could be applied to matter as well as light. In his 1909 lecture, Einstein had showed that there was a dual nature to light, that it can simultaneously have both particle and wave-like properties. Although it was a heretical idea, it was supported fully by experimental results. Inspired by the duality program initiated by Einstein, a young graduate student, Prince Louis de Broglie, remember de Broglie, his last name is spelled like Broglie, de Broglie, then speculated in 1923 that even matter itself can have both particle and wave-like properties. This was I think so. I think something like that. We'll keep going. This was a bold, revolutionary concept since it was. I'm not an expert of condensed matter. So superconductors, all those types of things are more of a condensed matter theory or condensed matter experiment type of subject. I don't, I am not an expert, so we'll keep going. Maybe it'll come out of this. Prince de Broglie then speculated in 1923 that even matter itself can have both particle and wave-like properties. This was a bold, revolutionary concept since it was a deep-seated prejudice that matter consisted of particles. So this whole, I think it's kind of coming back to me, this whole concept of like matter is matter and like light is light and light has wave like and both wave and particle like features, but then matter was more just matter and particles. I think this all kind of came to be regarded very differently because basically this Bose-Einstein condensate was acting. Well, the Bose-Einstein condensate was acting like a wave. Yeah, like everything in unison, depending on what you did to matter. This is so baffling. Yeah, it's kind of like if you cooled, the Bose-Einstein condensate, of course, requires you to cool it down to a certain temperature, to a very low temperature. But when that happens and things are at this low energy state, the atoms basically started to act like a single wave-like thing. I mean, bosons are named after Bose of Bose-Einstein, and photons are basically considered bosons at this time. Photon is an example of a boson. So, yeah. Thank you. Someone said, "What a beautiful cat." Ibrahimna, hi. So, yeah. But if the matter So Einstein liked the audacity of so yeah, matter waves comes from de Broglie. Einstein liked the audacity of de Broglie's matter waves and promoted his theory. So yeah, stimulated by Einstein's work on duality. So remember how there's no ether? I don't know if you mean ether like figuratively, right? So light does travel from A to B, as far as I know. That's how light gets to us from like distant objects. I don't know if that's what you're asking. Stimulated by Einstein's work on duality, de Broglie could explain away some of the mysteries of the atom by introducing the concept that matter had wave-like properties. Einstein liked the audacity of de Broglie's matter waves and promoted his theory. De Broglie would eventually be awarded the Nobel Prize for this seminal idea. But if matter had wave-like properties, then what was the equation that the waves obeyed? Classical physicists had plenty of experience writing down the equations of ocean waves and sound waves. So an Austrian physicist, Erwin Schrödinger, here he comes. Are you guys ready for Schrödinger? Yay! Was inspired to write down the equation of these matter waves. While Schrödinger, a well known ladies' man, was staying with one of his innumerable girlfriends in the Villa Herwig in Arosa during the Christmas holidays in 1925, he managed to divert himself long enough to formulate an equation that would soon be known as one of the most celebrated in all of the quantum physics, the Schrödinger wave equation. Schrödinger's biographer Walter Moore wrote, like the dark lady who inspired Shakespeare's sonnets, the Lady of Arosa may remain forever mysterious. Unfortunately, because Schrödinger had so many girlfriends and lovers in his life, as well as, oh my gosh, as well as illegitimate children, it is impossible to determine precisely who served as the nurse for this historic equation. Hi, Amazon must buy. What a player. I know, right? Is this sort of how the waves interact with each other and either amplify or null out the waves? No, so do you know about Schrodinger's equations? Um it's like a thing in quantum physics. And basically, well, let me read this again. Oh, hi. Hi, Sufyan. Hi. All right, welcome to the live, everybody. We have a new person. Amazon must buy is apparently Sufi. And then Molly said that she knows Russian, a little bit of Italian, a little bit of Spanish. Oh, goodness. Also British and Irish. Wow. Well, I did not know, guys. Well, I forgot because I read this book as a child. I forgot that Schrodinger is a player. I mean, I block things out. So I actually don't know. I don't know. I don't know anything, okay? But Schrodinger is very important in quantum mechanics. I promise we will study quantum mechanics on this channel because it's very important. It's not something that Einstein contributed or Einstein was much involved with compared to other things. And so that's why I think we have not come across it too much here. Reese said, is a sort of, wait, where was your other comment? I know nothing. Oh, shut up. You know things. You know things, Reese. I just think that I'm not explaining the matter waves very well. But we will get more clarity. Promise. Let's keep going. So Einstein liked the audacity of de Broglie, and then turns out that Schrödinger contributed something as well. And basically, you know how Schrodinger is famous for his work with like the Schrodinger cat thing, being there, not being there. We'll get into it. I'm sure it'll kind of come up here, and if not, we'll cover it from a different book. There's a quantum mechanics book that we can cover all this with. So anyway, we'll keep going with the story. So apparently there's some lady, and the Schrodinger equation came out of that or whatever, or after he was done with whatever. Anyway, over the next several months, in a remarkable series of papers, Schrodinger showed that the mysterious rules found by Niels Bohr for the hydrogen atom were simply consequences of his equation. So this is very nice in the sense that Bohr had done some work. So Niels Bohr, of course, another important person in quantum physics, had done important work. And if Bohr's results come out of Schrodinger's equations, then that's very important because, again, we want to be able to derive something something less fundamental from something more fundamental. So if you have, say, some equations that are sort of the description of the universe, and then you can derive something that you already know from that, then that's kind of how physics worked. That's how people basically made their careers as physicists. So for the first time, physicists had a detailed picture of the interior of the atom by which one could in principle calculate the properties of more complex atoms, even molecules. So within months, the new quantum theory became a steamroller, obliterating many of the most puzzling questions about the atomic world, answering the greatest mysteries that had stumped scientists since the Greeks. The dance of electrons as they moved between orbits, releasing pulses of light, or binding molecules together suddenly became calculable, a matter of solving standard partial differential equations. One young, brash quantum physicist, Paul Adrian Morris Dirac. Oh my gosh! I forgot about Dirac, of course. Okay, so guys, we have to study quantum mechanics on one of these live streams because there's too many stories there. There is too much that we have to cover, actually. But that's okay. So Dirac even boasted that all of chemistry could be explained as solutions of Schrodinger's equation, reducing chemistry to applied physics. So this probably kind of upset some chemists, but Schrodinger, he did really well for himself with his equations. So anyway, thus Einstein, who was the father of the old quantum theory of the photon. So remember how Einstein had given us the photoelectric effect and he got the Nobel Prize for that. So, I mean, coming up with a picture of the light, which had a wave particle duality enough to give us photons, which give us, electric current from the photoelectric effect. That's the old quantum theory. That's the old quantum theory. Got it? Like, that's when, it's like the old fashioned, like, quantum theory. It's not too crazy quantum theory. Whereas as it evolved, we got even more crazier quantum theory, like the whole Bose-Einstein condensate thing, the de Broglie stuff, the matter waves, whatever Schrodinger did, which we will study further in a different live stream. All of this was the new quantum theory, okay? So he became the godfather of the new quantum theory, Einstein, based on these Schrodinger's waves. Today, when high school chemistry students have to memorize the funny football-shaped orbitals that surround the nucleus with strange labels and quantum numbers, they're actually memorizing the solutions to the Schrodinger wave equation. So if you've taken chemistry with like the orbitals and the quantum numbers, like what he just said in the book, those actually come out of Schrodinger's equations. Does that ring a bell, Reese, or anybody else? Even Molly and Chloe might have actually seen this already. Elliptical orbit. So now we're talking about like the orbits around the nucleus instead of an atom. Those types, you might have learned about that in chemistry class. That's what the solutions of Schrodinger's equations is basically that. Make sense? Or at least I was trying to give a reminder, or maybe it rings a bell. We will cover it in more detail. So anyway, the breakthroughs in quantum physics now accelerated enormously. So, there was a time when quantum physics wasn't really a thing, and now there was sort of breakthrough after breakthrough in the 1920s and 1930s and onward. So anyway, the breakthroughs in quantum physics now accelerated enormously, realizing that the Schrödinger equation did not incorporate relativity. Just 2 years later, Dirac generalized the Schrödinger equation to a fully relativistic theory of electrons. And once again, the world of physics was dazzled. So, relativistic theory of electrons, because why not? While Schrödinger's celebrated equation was non-relativistic and only applied to electrons moving at slow velocities compared to light, Dirac's electrons obeyed the full Einstein symmetry. Furthermore, Dirac's equation could automatically explain some obscure properties of the electron, including something called spin. So now we're getting into spin, guys. It's very interesting, it's very important. It was known from earlier experiments by Otto Stern and Walter Gerlach that the electron acted like a spinning top in a magnetic field with angular momentum given by 1/2 in units of Planck's constant. The Dirac electron yielded precisely the spin 1/2 given by the Stern-Gerlach experiment. The Maxwell field, representing the photon, has spin 1, and Einstein's gravity waves have spin 2. With Dirac's work, it became clear that the spin of a subatomic particle would be one of its important properties. So this is something that we get into as well in quantum mechanics, which is that spin is sort of a fundamental property. And depending on what type of particle, you might have a different spin. And because Dirac worked on the relativistic equations for Schrödinger's equations, or for these matter equations, he was able to get this new property. So we have Dirac to thank for with the whole spin thing. Then Dirac went one step further. By looking at the energy of these electrons, he found that Einstein had overlooked a solution to his own equations. Usually, when taking the square root of a number, we introduce both positive and negative solutions. For example, the square root of 4 can be either +2 or -2. Because Einstein ignored a square root in his equations, his famous equation, E equal to mc squared, was not quite correct. The correct equation was E equal to plus or minus mc squared. This extra minus sign, argued Dirac, made possible a new kind of mirror universe. You guys ready? One in which particles could exist with a new form of antimatter. Yay! Are you ready for antimatter, guys? I know we did higher dimensions, but that's not enough. We also have antimatter, and honestly, I swear, antimatter is really not that bad, okay? Straight. I'm laughing at it's okay. It's the litter robot is starting its cycle, so that's why everybody is looking up. But okay, antimatter, guys, all right? Strangely, just a few years earlier in 1925, Einstein himself had entertained the idea of antimatter when he showed that by reversing the sign of the electron charge in a relativistic equation, one can get identical equations if one also reverses the orientation of space. He showed that for every particle of a certain mass, there must exist another particle with opposite charge but identical mass. So it's just opposite charge and why not? As if this isn't complicated enough, let's look at antimatter. Reese, it's very simple. It's very simple. You ready? Electron's antimatter is a positron. Just think, if you ever get confused with antimatter, then just think electron, positron. Simple. No, seriously, it's just a plus minus sign thing. I'm telling you, antimatter is not that bad. I'm telling you. I'm telling you. It's just for every particle. Sorry. My phone might be okay, whatever. No, there's charge. For every particle of a certain mass, there must exist another particle with opposite charge but identical mass. So listen, it's just electron, positron. So if you're ever in doubt, just remember electron has a certain mass and has a certain charge. Positron is the same mass as the electron, but it has the opposite charge. So it's like a positive electron. That's it. So like a seesaw kind of thing. Yes, antimatter is not that bad, okay? So like in the particle physics experiments, sometimes an electron really what could be involved in the interaction is really a positron. You know what I mean? Basically, if it's like, depending on the plus or minus sign, it could be like an electron but with a positive charge, so it would be a positron. Now in regular matter, we generally have the regular matter version, like the electron version, but in a, say, very excitable or very different kind of, or a sort of an exotic interaction, we might have the positron instead. But the more stable, matter is really the electron. But the concept of antimatter is simply the same particle. If it's a fundamental particle, just imagine there is another particle, it's antimatter, which, you know who's really good at all this is the Feynman lectures. We should also study that. Basically, depending on, in the Feynman diagrams, do you know the Feynman diagrams? Depending on, depending on which side you're coming in, depending on your charge, you're either a matter or you're antimatter, okay? So if you forget about antimatter, its definition, just think electron, positron. There is electron with the negative charge, then there's a particle of the same mass as electron, but with the positive charge, okay? It's not that bad. It's not like higher dimensions. It's very simple compared to higher dimensions. Okay, so so he showed that for every particle of a certain mass, there must exist another particle with opposite charge but identical mass. Relativity theory not only gave us the fourth dimension, it was now giving us a parallel world of antimatter. However, Einstein never wanted to quibble over priority, graciously never challenged Dirac. So basically, Dirac is the one who is credited for antimatter, but basically this antimatter thing comes from the E equals to mc squared thing. You know what I mean? So, or that's what the author is saying anyways. At first, the radical ideas of Dirac met with fierce skepticism. So, by the way, a lot of these people who are talking about parallel universe and another whole universe, oftentimes they actually mean antimatter. What they mean is there is the regular matter that, you and I are made of. We're made of ordinary matter, just very simple, boring stuff. Electrons, protons, and neutrons is what makes us, right? So, because we're made of atoms, we're made of the normal elements. Quite a large mistake on the part of Einstein. Sort of. He kind of forgot about the minus side of things. Don't think math was his cup of tea. It really wasn't. Poor boy. Poor Albert. Poor Einstein. It really wasn't his cup of tea to do the math or, but honestly, when you're doing that much math, as a physicist especially, you're going to miss some stuff. That's the thing. What people don't realize is like when you play basketball, you actually have a lot of misses. This is kind of like that. He played basketball, so don't expect him to just only be able to get it through the basket. Sometimes he missed a lot, and that's part of being human, and it's okay. Successful people actually have a lot of failures. They make mistakes because anytime you're doing something a lot, you're going to make a lot of mistakes, and that's okay. That's okay. Some people are a bit more perfectionist. I will say, some people are more perfectionist. They want to perfect the one thing that they want to do. But not Einstein. Just think about it. He's so prolific. Just think about Einstein's contributions. It's so many things, right? He contributed, I mean, just in 1 year, he contributed like 4 things. Yeah, and he did a lot of stuff. He did a lot of stuff. Then he had the Bose-Einstein condensate. He had general relativity. He tried for the grand unification theory, which is still not really complete yet, but he tried. And then he's talking about, because of the relativistic thing happening with Schrodinger's equation, we got spin. Now we're getting antimatter because something he forgot and Dirac remembered. It also gives other people opportunity to contribute. Honestly, sometimes when you are very prolific, it's good to just not be a perfectionist, because whatever mistakes you're making or whatever gaps you are leaving in your work, it gives other people an opportunity to contribute. This happens within our work too. I've worked with people where, like, did you read my comment? Mistakes sometimes provide answers. That's what makes us brilliant. Yeah. Sometimes I have contributed to a project and my colleagues said, it's okay, this part you didn't do it because that part I did it. And it gave me an opportunity to contribute. Sometimes you get something to a certain level and then someone else can do that thing. So he actually gave Dirac an opportunity to contribute. And now we know Dirac's name because of Einstein and Schrodinger, honestly, because of what Schrodinger contributed, and then what Dirac picked up from there is how we got the Dirac equations, which is the relativistic quantum stuff. Okay, so there's also antimatter. It's not too bad. It's not too bad. At first, the radical ideas of Dirac met with fierce skepticism. Oh yeah, so I was saying, people seemed to be very overthinking about this antimatter stuff. Like there was so much sci-fi about this, and people were like, oh my gosh, if there is matter, like that's what we are made of. And then there is a whole family of the antimatter. They kind of made it into a big deal, and they were very like critical of it, So anyways, at first, the radical ideas of Dirac met with fierce skepticism. The idea, what time is it? It's 1:15 in the morning. Okay, good. The idea of an entire universe of mirror particles that arose from E equals mc squared, plus or minus, of course, seemed like an outlandish idea. Quantum physicist Werner Heisenberg, oh, remember Heisenberg? Who with Niels Bohr had independently found a formulation of the quantum theory equivalent to Schrodinger's, wrote, "The saddest chapter of modern physics is and remains the Dirac theory. I regard the Dirac theory as learned trash, which no one can take seriously." Are you serious? However, Kato. Hi. So, um, apparently Heisenberg was very critical of Dirac. But Jesus, he also contributed to all of this. So I'm just surprised that he was so critical of Dirac. However, physicists had to swallow their pride when the anti-electron or positron was finally discovered in 1932, for which Dirac later received the Nobel Prize. How is that? Ha ha ha. Wow. So, by the way, so many crazy things have not been confirmed or discovered, but positrons actually are discovered. They are a real thing. They can be made in different interactions, and they're not that crazy. Antimatter is not that crazy. I just, I can't believe it. Wow. So Heisenberg, probably, I don't know, probably in an accelerator or something. I forget, but it's a thing. Heisen. I can't believe how critical Heisenberg was. Yeah, yeah, it's probably in a collider type of experiment. Recently at CERN, they found new ones. Good. Yeah, I mean, how crazy, right? The stuff between quarks. Oh, good. Oh my God. I think positron, correct me if I'm wrong, but I think positron was the first antimatter to be confirmed, right? Because there's others. There's other stuff. Good night, Molly. I'm going to bed. Good night, y'all. Oh man, this is probably way past your bedtime, Molly. Miss Connecticut. Good night. Good night, my love. So, I cannot. I can. Is Chloe going to bed too? So, I cannot believe this. How critical was Heisenberg of Dirac? Poor Dirac. Oh, poor thing. Okay. Bye, Molly. Bye. See you next time, okay? Have fun. Heisenberg finally admitted, I think I think that this discovery of antimatter was perhaps the biggest jump of all the big jumps in our century. Once again, the theory of relativity yielded unexpected riches, this time giving us an entirely new universe made of antimatter. Oh my God, because remember that Dirac got antimatter because he dove into Einstein's equations, he dove into Schrodinger's equations and derived, so Dirac derived the relativistic form of Schrodinger's equations, which were written for matter, and also discovered that that yielded something called antimatter, which would have come from the E equals mc squared stuff anyway, because that's done with a square root. So it's really plus or minus mc squared. And so Dirac got antimatter. People made a big deal of this, like saying, oh, there's a whole universe of. Antimatter is really not as big of a deal as people first thought of it. I think people at first were like, oh my God. So if all the matter has an antimatter, then is there like another whole universe of this stuff or what? We am alien. Okay. So people made a big deal of it. But honestly, it's not that bad, dude. It's just a thing. It's not of all the things in particle physics, it's really probably not the craziest stuff. It's not that bad. And, in all the in especially probably like these exotic or more rare particle physics interactions, you might get a little bit of positron. Like, why not? But actually, I think like for example, I worked on an experiment for my PhD, and I remember having to kind of explain something at one point where there was a charge asymmetry because basically the interaction was making more electrons than positrons, but it was still making positrons. It's just more electrons were being made, and so overall it had a negative charge. Because if you made equal amounts, say in an interaction, if you made equal amounts of like electrons and positrons, then you would have neutral charge. But if you make more electrons, then you would have a negative charge. And actually, that charge is kind of important because then it leads to other things and whatnot. So, oh, I have figured it out. Okay, good. Great. Great, great, great. So, anyway, moving on. We also got antimatter now, which came out of Dirac's work, who made Schrodinger's equations relativistic. So it seems strange that Schrodinger and Dirac, who developed who developed the two most important wave functions in the quantum theory, were such polar opposites in their personalities. While Schrodinger was always accompanied by some lady friend, Dirac was painfully shy with women and was a man of remarkably few words. Good. Dirac was a good guy. After Dirac's death, the British, honoring his contributions to the world of physics, had the relativistic Dirac equation engraved into stone in Westminster Abbey, not far from Newton's grave. Oh, my baby Dirac. He died with his equations. Soon, physicists at every institute on this planet struggled to learn the strange, beautiful properties of the Schrödinger and Dirac equations. However, for all their undeniable successes, quantum physicists still had to grapple with a troubling philosophical question. If matter is a wave, then precisely what is waving? This is the same question that had haunted the wave theory of light, which gave birth to the incorrect theory of the ether. A Schrödinger wave is like an ocean wave and eventually spreads out if left by itself. With enough time, the wave function eventually dissipates over the entire universe, but this violated everything that physicists knew about electrons. Subatomic particles were believed to be point-like objects that made definite jet-like streaks which could be photographed on film. Thus, although these quantum waves had near miraculous success in describing the hydrogen atom, it did not seem possible that the Schrödinger wave could describe an electron moving in free space. Hi, guest not found. Hello. In fact, if the Schrödinger wave really represented an electron, it would slowly dissipate and the universe would dissolve. Something was terribly wrong. Finally, Einstein's lifelong friend, Max Born, oh, thank God, proposed one of the most controversial solutions to this puzzle. So Max Born is another Max that we like. In 1926, Born took the decisive step. Claiming that the Schrödinger wave did not describe the electron at all, but only the probability of finding the electron. Look at that. It's not the electron, guys. It's the probability of finding an electron. How naive of us to think that it's the electron. Are you serious? He declared that the motion of particles follows probability laws, but probability itself propagates in conformity with the laws of causality. In this new picture, matter indeed consisted of particles, not waves. The markings captured on photographic plates are the tracks left by point-like particles, not waves. But the chance of finding the particle at any given point was given by a wave. Got it? More precisely, the absolute square of the Schrödinger wave represents the probability of finding the particle at a specific point in space and time. Thus, it did not matter if the Schrödinger wave spread out over time. It simply meant that if you left an electron by itself, over time it would wander around and you would not know precisely where it was. All the paradoxes were now solved. The Schrödinger wave was not the particle itself, but represented the chance of finding it. Okay, I have to charge my phone. 1 second. I'll give your brain a little bit of a rest and we'll continue, okay? It's just the probability, guys. It's okay. You know, quantum is of the small stuff, right? Well, it's the small stuff being observed is reported with its probability, not it. Okay? Probability solves everything. I'm realizing we need to have a class on quantum mechanics. With that, we will be able to solve these troubles. But let me charge my phone for a little bit. We can keep chatting. Oh, well, this is so much fun. Hi, Fuji Babu. Hi. Hi. Hi, Fuji. Fuji says, what is the probability of stopping the kisses? No chance, Fuji. That is the face my brain is making. Why? Reese, how are you doing now? Recovered? Okay, Reese, have you absorbed higher dimensions and antimatter? How are you feeling about the higher dimensions and antimatter now? In the meanwhile, I will find you Schrödinger's equations, okay, so that we can look together. It's really not that bad. It's really not that bad. See, I have this book. It's called Quantum Mechanics by Peebles. Student, that's my name. Thank you for reading. Happy weekend to Baji and all science friends. Interesting baryogenesis. See you next time. Hi, Ki, you're leaving us. I have to be spoon-fed these concepts at a snail's pace as I'm an idiot. No, you are not. We're covering a lot of different topics, Reese. It's fine. Don't beat yourself up. We will cover it all again. Today, I just wanted to show you Schrödinger's equations so that we don't leave this off without seeing what these equations look like, since they're so important. I'm laughing myself because we're covering a lot, you know? So, but what do you think of the antimatter? I do think that today's concepts of antimatter, higher dimensions, and right now, what is it that we covered just now? The probability. Honestly, the antimatter and the probability are not that bad. It's really not that bad. I promise. It's going to be great. There it is. Psi. Fuji. No Fuji. Coronation. I am looking at this. This is a good book of quantum mechanics, by the way. We will study this. I need to get a camera and a whiteboard, probably, to write these down properly. But Just wanted to show you. So, yeah, so here. This is, by the way, Quantum Mechanics, the book by P.J.E. Peebles. So you can also get it yourself. It's published by Princeton University Press in Princeton, of course, New Jersey. All right, single particle wave equation. See, when it comes to Schrodinger's equation, you can look at the single particle wave equation. So Schrodinger in 1926 wrote down the differential equation satisfied by the matter wave associated with a non-relativistic. So this is just a non-relativistic particle moving in a potential well. He was guided by an analogy Hamilton had noted between the motion of a particle in classical mechanics and the short wavelength limit of the motion of a light wave in a medium with index of refraction that is a function of position. So Hamiltonians, when you learn classical mechanics, you have to learn Hamiltonian mechanics. Hamilton is the guy, Hamiltonian is the, thing that the equation. And so so Schrodinger was not starting from scratch. None of these guys are, starting from scratch. We already have Hamiltonians from classical mechanics, and Schrodinger is kind of doing something similar. So for quantum mechanics, okay? So this is de Broglie's equation, by the way. This psi, a wave with energy E oscillates with a frequency of omega, where omega is given by E over h bar. That's that. And then at some point, you can get the more general time-dependent Schrodinger equation. I'm just showing you while we're standing here charging the phone, is that one. So see, it's quite simple. It's not too bad. It's pretty, small. I h bar partial psi partial t. So the partial derivative of psi with time, h minus h bar squared over 2m delta squared plus v, that's the potential, into psi. So, he did something with basically putting together that equation. And this is for a non-relativistic particle that's moving in a potential well. Okay, so once you study all this, it's actually not that bad. It's just, honestly, quantum mechanics actually starts with the way quantum mechanics is taught, it's actually easier than classical mechanics. I'll show you. The equations are actually easier. The equations are actually easier. Because in the beginning, in quantum mechanics, you're just learning it for a single particle. Like you write down all these equations for a single particle in a potential well. That's not that bad. And that's probably what Schrodinger started with too. So it's fine. You can do it. Like like quantum mechanics, because quantum mechanics is for particles, right? For small things. So you don't even have to consider like a multi-particle, multi-body object or many objects. In the beginning, you're really just writing down equations for a single particle. And then where, right? Single particle in a potential well, in an infinite well, in a finite well. It's literally, I don't even know what that, okay. I see. Okay. So what I mean is, so what is mechanics? Basically, we want to know and predict the position of something with respect to time. Position of a body, say, as a function of time. Do you follow me? Classical mechanics is, say, understanding the position of, let's just pick a couple of planets. Let's just say we like Mars, even though my favorite planet is actually Venus, but whatever. Mars is position with respect to time or as a function of time around the sun is, trying to figure that out and coming up with equations to write that down is an exercise in classical mechanics, for example. Quantum mechanics is more to do with trying to understand how a single particle moves within some field, some potential, something. We consider, at first we think of an infinite well, like a potential energy. Just like there's potential energy in classical mechanics, we consider something like that in quantum mechanics as well. And so it's kind of like now we're not talking about the heavenly bodies, we're not talking about Mars or the sun. We're talking about understanding how a small particle behaves and trying to understand its position as a function of time. So think of it as quantum mechanics, right? Quantum mechanics. What's mechanics? It's like sort of like movement, right? Like a car moving, car mechanics, right? The people who can fix cars. Car is something moving. Its position as a function of time is something we would like to control, for example, when it comes to cars. Quantum mechanics is basically trying to understand what will be the position of a particle as a function of time. That's it. That's it. It's not that bad, I promise. Okay, so I'm reading the rest of this. I'm thinking we can continue this tomorrow. You guys, are you going to be here for the live stream tomorrow night, same time? Or should I do it earlier? What do you think? Because this chapter is a little bit long. And the rest of it is quantum. So what we might do tomorrow is I might just finish this chapter tomorrow, first of all. It's going to be more to do with quantum physics. And I can also start with a little bit of a summary of what quantum physics and quantum mechanics is so that we can kind of ground ourselves with that. What do you think? Okay, I'm playing snooker. What about, like, should I do it at this time? Which is like your morning? Did the quantum mechanics explanation I gave make sense? Make a little bit more sense than before? Does that help? Let me type. Yeah, it made a bit more sense. I have to do some research in my own time, try to understand. We can cover it more tomorrow. Thank you, Heike. Thank you for being here. Thank you so much. Oh, were you awake all night, Reese? Oh, that's. Did you not go to bed today? Oh my gosh. Are you playing snooker like competitively tomorrow, or you probably need some rest? Huh? Are you like a competitive snooker player? No, haven't slept. Probably for days. An hour or two here and there. Oh gosh. Well, that's not good. How was your meeting the other day for your business? Is it up and running now? Thanks for watching. Thanks for watching and listening, everyone. Thanks for watching and listening, everyone. Not competitively, just with my brother. I don't see him much as he lives in a different part of England. The meeting went very well, thank you. The lady was very impressed with the work I'd done. Oh, good! Congrats! Congratulations, sounds good. You should tell us more about your components, electronic component work as well, if you want. That's awesome. Thanks for sharing from your own experiences as well. Enjoy. Enjoy time with your brother. Tomorrow, so I think what happens is also that these topics, it helps to hear the same thing or a similar, sort of the same topic more than once. Because remember, I mean, a lot of people who are like fluent in these topics have dealt with it a lot. They've repeated them. So if it feels a little bit confusing now, that's because maybe you heard it for the first time. We will cover these things again tomorrow and look at it again, maybe in a different way, and that might help. Over time, we'll gain more comfort with these. It's not really comparable to anything. But that takes a very basic understanding of these electronics, like capacitors and inductors, right? Things like that. Is that what you mean at the component level? Like, do you have to fix capacitors that are broken or replace them, or inductors that are blown? Stuff like that? Or resistors? Things like that. Is that right? Because that's very much a part of my world too. I actually worked on electronics myself at one point. I'm not like a big expert in them, but I had to assemble a certain board for my experiment. Yes, switch mode, power supplies, and understanding how they work. Oh wow. Cool. I actually wrote a paper in on an electronics topic. Maybe I can send, or maybe I can share that with you. Here, let me look it up. I have a paper on this, guys. Well, I have a paper on other things too, but I have a paper especially on an electronics topic that you might find interesting. Let me give you my tough paper. Actually, I have a video on it too. Wow. So if you go to archive.org, if you're interested, you don't have to go to archive.org, but if you're interested, I actually was the corresponding author on a paper that you might give your opinion on. It's called Dynamic Tunable Notch Filters for the Antarctic Impulsive Transient Antenna, ANITA. And I am the corresponding author on it. So I wrote this as a grad student. Maybe you'll find it interesting. It's my only instrumentation paper, actually. But a lot of people don't have any, so I'm kind of proud. I did instrumentation, I did hardware, I did software, I did analysis, simulation, so I was very well-rounded in grad school. Yay! Did you get that? Dynamic. Oh, let me just type it. Oh, you know what? I can even share this. I'm crazy. I can just share I can copy this link. I'm a cray. I forgot that I have the internets. It's probably simple stuff for you who's dealing with electronics all the time. But yeah, no. Electronics is a part of our world too. And that will tell you about my PhD topic as well. My PhD was in this ANITA experiment, Antarctic Impulsive Transient Antenna. I'll have a look after I've screenshotted it. Okay. Can you go to the link that I just shared above? Does it let you go to it? And then it goes directly to the... So I gave you the archive paper. It's in a journal too, but the journal costs money. They don't pay us anything, the authors, but the official journal paper... Oh, dear God. Oh, that's not good. Huh. Okay. Okay, I'll copy the title of the paper and put that in too. That's the paper title. Oh, thank you. Okay. So anyway, this paper, there is a journal version of this. I wrote this for NIM. What's it called? National Instrumentation and Measurements. That's the journal that this is in. But I gave you the archive link because the archive one is free. In academic journals, when you publish, they charge you money as the author, and they also charge the reader money. And only the journal gets richer. So that's why academics started this thing with archive, where we can upload the paper. We basically upload the draft version to archive as it's still going through review, and then we update it later on once it gets accepted in the journal. But yeah, that's my one electronics paper. I have papers that are on like analysis and stuff more, but not as much on electronics and instrumentation. But instrumentation is very important in experimental science. So yeah. Okay. Okay, we'll continue our quantum mechanics discussion tomorrow, which will also aid in our discussion of the rest of this chapter, which goes into quantum physics, okay? So yeah, we're gonna do that. We're gonna do that tomorrow, same time-ish. Get some sleep tonight. Get some sleep today. Even if amazing lady. Oh, thank you. Bafflingly brilliant. Oh, thank you, thank you. Oh gosh. I was a youngin' when I wrote that paper. Very, very much in hopes of a bright future. But, I think it's good to review things once in a while and get back to a problem with a new perspective. Because after my PhD, I did other jobs that are not as related to my PhD work or my core physics work. It's related, but not the same, not pure science. And now I'm kind of getting back into it with the pure science and the pure physics. And you guys are part of this journey. So thank you for being here. And your encouragement is very, supportive for my journey here. Because I basically spent like 6 years working in like more real jobs after my PhD. And I don't know. Then I was done. So even though I was kind of using my background in physics, I wasn't using it to do pure physics research anymore. And I learned about a whole new other world and field and everything. And then I've decided to kind of go back to my more physics-y roots now. And honestly, I'm reminding myself of a lot of these topics as well, along with you. And hopefully I can get deeper into some topic that I hadn't really done. Because, in a PhD, you get very specific into one subtopic. And honestly, like I did my PhD in neutrino stuff, right? It's a different particle, lighter and neutrally charged cousin of the electron. It's a type of lepton, and its search from sort of these higher energy natural particle accelerator type of environments is what I worked on for my grad school. So I didn't do anything with dark matter or dark energy, for example, not really directly anyways. So what I was saying is basically when you do a PhD, you get to know a lot about something, but there's other parts that you kind of have to neglect. So I'm kind of going back into yeah, you should be working for NASA or something. Yeah. Well, even NASA can have strangely normal jobs, actually. It really depends on the position that you get. Even NASA jobs can be, I don't know. I know people who work at NASA who just do meetings all day, like they don't, like as you get more senior, I think the problem is I got more senior. As you get more senior, you get farther and farther away from the cool stuff. You have to do meetings and admin-y stuff as you become like more of a sort of a leader of things, So there's people who are physicist background working at NASA who not necessarily really doing physics, So it's hard. It's hard to know exactly what you'll end up doing in a role ahead of time. But it's a good suggestion. I did work on my PhD project was partially with NASA. It was an NSF and NASA combined project. So that's why I do know about NASA to some extent, and I know that there are people at NASA who have had the same problem that I did when I was working these more quote unquote normal jobs. But yeah, I'm on a journey now to figure out my sort of next type of role if I'm gonna get back into doing a job role type thing. So we'll see. But I think getting back to physics and understanding it and seeing the whole bigger picture of things from a new perspective is very helpful. That's why thank you for being here. It's helpful for you guys to be here as well. Hi, Polly. It's all dark now. All right, guys. Aw, love being here. Don't understand. Don't understand a lot of what's discussed, but I enjoy it nonetheless. Aw. Thank you. Thank you, thank you. Yay. Yay. I think you understand really well, actually. You help to keep the conversations engaged and everything. It helps a lot to have you here. Universe is like Matrix. Maybe. I don't know. I haven't seen The Matrix. Is it a good movie? I actually have not seen The Matrix, guys. For being a scientist, I'm actually I don't really like sci-fi much. Didn't get into it too much. I'm glad to have caught your live. Thank you for the stream. Thank you. Thank you for being here. Wow, you should watch The Matrix. I'll watch it if someone makes me. So there's movies that I watch on my own volition, and then there are movies that I expect somebody to make me watch, and then I watch it. It's a simulation theory, basically. Like simulating what is it? Like, what's the main story? It's simulating something on a computer, like our life, or what? Oh shit. I accidentally stopped the... Yeah, a simulated existence on a computer system. And the main guy is like unplugged from the simulation and goes into the real world. Oh, it's a simulation existence on a computer system, And the main guy is like unplugged from the simulation and goes into the real world. Oh, okay. Okay. I think I get it. Got it. Thank you for telling me what it's about. Didn't even know about it. Nobody made me watch it. Oh, Heike. I've watched 5 times. You can watch them many times and find them interesting. Oh, you've seen it 5 times, Heike? Wow. It's like a battle between the computer simulation and the real humans. Okay. Sort of like Skynet in the Terminator. Guess what else I haven't watched? It's the Terminator. It's almost like I'm very compartmentalized. I keep my physics and science compartmentalized from my entertainment, from my like movies and music. I don't know. I'm very compartmentalized. Oh, come on. You haven't seen that? No, I haven't. I don't think I've seen the whole thing. That's what I got my name from. Really? Is there somebody called Reese in the Terminator? Like, I might have seen the Terminator like bits and pieces. I definitely don't know the story. I haven't seen the full thing. Does it have that Arnold guy in it? Terminator? Is that Arnold Schwarzenegger? Does the Terminator have Arnold Schwarzy, whatever? Is that what? Yeah, Reese Kyle on the Terminator. Okay. Okay, good. But like, who's the actor in it? I'm trying to remember if I've seen bits and pieces of the Terminator or not. I haven't. Another one that nobody made me watch. I'm so sad to be so ignorant. But not really, because I have not been motivated to watch it. Just continue to be ignorant about it. Yeah, it's Arnie who's the Terminator. Okay, I think I've seen parts of it then. I've seen parts of Terminator. There are 4 movies: Matrix, The Matrix Reloaded, Matrix Revolutions, The Matrix Resurrections. Okay, and then Terminator. Got it. Only The Matrix 1 is good in my opinion. It just got a bit crazy after. Okay. Okay. That's funny. I don't know these things. Wow. Yes, it is like science. Okay. Wow. Got it. Well, Heike, did you sleep today or are you also going to bed now? You guys, it's early morning for you. Well, actually, I guess I guess morning for you. Good morning, Heike and Reese. Welcome to November 9. Well, that reminds me, I have somebody's birthday today. My cousin's birthday is today. Or not today, tomorrow. Have you not seen? Here it's 9:40 in the morning. Oh wow, that's late. Have you not seen Contact? I have not. I have not seen Contact. I have not. I'm so sorry. I'm the worst when it comes to Hollywood. I'm more of a Bollywood person, you know? Instead of the election watch party, I should have done a sci-fi movie watch party, actually. Oh, that's your favorite film? Contact? Wait, is Contact is not E.T., right? Contact is not the same as E.T., correct? Is E.T. a different film? Because I've also heard of E.T. and have not watched it. But in my defense, I think E.T. came out before I was born. I don't know. Something like that. I've not seen Contact. Have I? I don't think so. Is it to do with aliens? Aliens contacting us? No, it's sort of about radio telescopes and messages from an alien race. It's good. The main character works at the VLA, I think, very large area. Oh, good. Oh, I might like that. I used to work on a radio. Basically, I used a radio telescope in my experiment, so I know about radio arrays and things like that. That would be interesting for me to see. Okay, yeah, I don't think I've seen it. Contact. I should definitely see it. I'll probably love it. I love those types of things, like where it has like a science, you know, experiment. But like, I don't like it when it's too sci-fi-y, like too like unreal. It has to have a good flavor of science in it for me to like it. You would love it, I'm sure. Okay, I'll try it out. Okay, I need to see it. Okay, where is it? How do I find it? Is it on Netflix? Currently, I just have Netflix. That's it. I don't have Contact. Or I don't have whatever else. I said I don't have Contact. I don't know. Maybe I have access to it somehow. I have to look it up. I have to look at it up it. I need to look at it. I need to look up it. Look it up. Look up it. Did you see it on like a DVD? Back in the DVD days? It's the most believable scientific alien movie. That's why I like it. Oh, good. I had to buy the DVD. I don't think it's on Netflix. Yeah, that's what I thought. Like, you probably saw it on DVD. Alien movies is also good. Okay. It's a Jodie Foster one. The Lady from Bugsy Malone, Silence of the Lamb. Okay, I think I know Jodie Foster. Okay. Got it. Got it, got it, got it. Okay. Thank you guys for the movie recommendations. I think I definitely need to see Contact. I think that's the one I'm missing super duper at this point. Jodie Foster, Lady from Bugsy. Okay, awesome. Thank you guys. I'll let you catch a few winks. Maybe you can get some sleep still. Um, go get some rest and join me again tomorrow. We will finish that chapter we were on with the quantum physics and the grand unification theory. And we will look into a little bit of quantum mechanics base foundation knowledge, or just a little bit of an introduction to quantum mechanics for us tomorrow to start the discussion. But please do join us again tomorrow. Otherwise, it's like kind of boring and a little bit sad for me to talk about the physics and nobody else cares. But when you guys are here, a lot of you, it's very nice and very encouraging and a great discussion. So thank you again for being here, and hope to see you again tomorrow. Bye, guys. Good night. Good morning. Bye bye.